The Ben Heck Show is brought to you by Element 14, the electronic design community and online store built for engineers and hobbyists alike. Join now and browse the store at element14.com.
In the year 2000, Ben Heckendorn built his first mod.
We can rebuild it. Smaller, better, portable.
Since then, he has continued his work, helping those in need with creative new projects. Got an idea you'd like to see built? Why not send it to the Ben Heck Show?
Hello and welcome back to the Ben Heck Show. In this episode, we're going to be taking our hats off to the community and answering your questions and comments. We'll also be spending some time working on my new pinball machine. We'll start by addressing some comments and ideas from the Element 14 community. One popular area of discussion is how we're going to finish our automatic can crusher. Here's some of our latest ideas.
So the first can crusher we did, we had the can there and we tried to crush it using a big giant solenoid, which is kind of what's on a pinball machine. It was basically a huge electromagnet which is going to cause the rod to go and use a plate to smash the can flat.
3, 2, 1.
But that didn't really work out. So one of the things we thought about, or tested at the end of the episode as well, was using a stepper motor to drive it. A stepper motor is, what you have on a CNC machine. It's a motor where you send it pulses through a driver and it rotates in exact increments in either direction. And it also has a lot of torque. It allows, on a CNC machine, for instance, the bit to cut through the wood. So the idea was to create like a multi-stage cartridge like this. And then you would have basically 3 stages to it. This would be a rotating drum. The can drops in to that stage. The drum rotates via a stepper motor, and it goes into this stage. Now on that stage, the cross section would look like this, right? The can would be here, and you would have a piston of some type, like this. And this would be actuated by a stepper motor, so it goes, which would cause this to go in and out and crush the can. Then finally back in this one, after the can's crushed, this rotates again to this stage where the can falls out into the garbage.
Next up is a discussion about CNC machines. Michael Strong writes, having seen the ShopBot on Ben Heck's show, I was wondering how it compared to the mini CNC router he made. That's a smashing question, Michael. There are many kits available in the sub $1,000 to $3,000 range, or you can look for a complete turnkey solution starting around $5,000. One popular solution is the MakerBot. You can buy complete kits for around $1,000 or just the frame for a couple hundred. This is a 3D printer. It creates objects by depositing multiple layers of extruded plastic. This is considered an additive process. The kind of CNC machine you see on this show uses bits to remove material, a subtractive process. Kits for these start at a few $100s and get more expensive with features and complexity.
Okay, I'm here with actually my shop neighbor, the next shop over, David McPherson.
Hi there.
And I heard him routing when I first moved in. I came over, I'm like, oh, he's got a router too, so why don't you tell us about this router you have?
This is a Shark CNC. I bought it from Rocker Woodworking. I've had it for about 2 years. I've been doing woodworking for a while, and when I found out what a CNC could do, I just absolutely wanted to have one. And so I did some homework, and there's a few lower priced models, but they don't nearly compare with the capabilities of this one.
Because you get a whole package.
You get a whole package, it's just out of the box. A few screws, and you put it up and plug it in, and you're ready to go. It comes with a $600 program, which is very intuitive and very extremely easy to learn.
One big difference between do-it-yourself and commercial is the software. When you make your own CNC machine, you often have to find your own G-code interpreter, or perhaps the software itself that runs the machine. It can actually cost more money assembling the components than getting a complete solution. However, if you spend more money and get a complete turnkey solution, you get everything you need, software, G-code interpreter, the whole shebang, and it just works right out of the box. Our final comment from the Element 14 community comes from Her Sir Smiley, who writes, The small error that I would like to cite is you refer to the microcontrollers in your build as microprocessors. Although this is a minor error, I feel it should be addressed. A microprocessor is a CPU or brain and they can be purchased. Microcontrollers are somewhat complete mini-computers. Microcontroller chips such as the Parallax Propeller, PIX, and the Atmel series of chips, also called Arduinos, are able to access the built-in microprocessors to handle the code programmed onto the chip memory. This code can then be transformed into the ability to use other peripherals on the chip, such as extra memory, oscillators, timers, signal drivers, and logic gates. These peripherals are what allow the microcontroller to act like a small computer, and many microcontrollers contain multiple microprocessors to allow for even more actions to happen at once. Again, it is a small error in naming, but should be noticed. That was a very detailed explanation. Thank you, Michael. The moral of the story is that microcontrollers act like their own little computers, where microprocessors require many other external parts. Now let's move on to the YouTube channel questions. The first one comes from Sega Fanatic 5188, who writes, in regards to the Sega CDX Portable, "This kind of stuff sort of makes me mad. The CDX is a bit of a rarity. It really didn't deserve being destroyed like this just to be made into a portable. If it was a system that was still in production and abundant, that'd be one thing. But these aren't being made anymore. There are only so many out there, and when they're gone, they're gone." That is certainly a good point. However, I would like to point out a few points of my own. For one thing, yes, the Sega CDX is rare, but you can still get one for under a couple $100 on eBay, so it's not astronomically rare. It is quite unlikely, in fact probably impossible, that I myself would ever completely destroy the existing stock. I would get bored of doing it long before it would happen. Zingazol asks, also about the Sega CDX, "Cool one, but why is there no lid to protect the spinning CD and the infrared beams?" Ah yes, well, we only have 2 weeks to produce each episode, so we ran out of time. The Techman Sam asks, "Why does he say multimeter like that? Garg." Well, I think it's a byproduct of how I say potentiometer. Potentiometer, multimeter. Also, multimeter just sounds boorish and provincial. The Sweden Movie asks, "You rocks, why you not my dad?" Probably because I never met your mom. Josh the Freerunner asks, "This is awesome. Did you go to a school of engineering?" I did not actually go to engineering school. It's all self-taught, and I have many piles of dead electronics that will attest to that fact. I do, however, have a background in graphic arts, which helps me with my layout and physical design of objects. Finally, we have a suggestion from Zach Blakely, who writes, "Hey Ben, I recently discovered your show and think that it would be interesting to see a desktop computer built into a metal suitcase. This would need to be as compact as possible, yet things like the graphics card would still need to be on board. I also imagine you have a fan for intake and another for sucking the air out again." That is a project type we've discussed doing before on the show. The basic thought is that if you were a LAN gamer, you could take this self-contained computer to the LAN events with you and set it up quickly and be ready to pwn before anyone else would be. Now it's time to take a break and thank our sponsors, Element 14. If you've watched the show in the past, you've probably heard me refer to their online community, and you've just heard some feedback from the forums there. It's a grand place to do research, ask questions, find answers, and meet up with like-minded professional engineers and hobbyists. In the coming months, Element 14 will be making a number of improvements and enhancements to both the community and the online store. This is yet another example of their commitment to the culture of electronics. And if you so happen to be in the San Francisco Bay Area this May, don't forget to stop by the Element 14 booth at the Embedded Systems Conference from May 2nd to the 5th, and also make a fair on the 21st and 22nd. Now, back to the show.
Okay, the next thing we're going to work on with the pinball machine is the lights on the board, and we're going to use a matrix for that. Not the matrix, just a matrix. So there's columns here and rows here. Now what we do is we have 16 bits of control for the columns and 8 bits of control for the rows. Forgive me if I don't have the right number here. Most pinball machines use 8x8, but I'm using more, so I can address up to 128 lights. And the good thing about this is we can address 128 lights with 24 wires instead of having like 28 different wires. So on our motherboard, we have this variable here. Let's say it's one word, 16 bits, and then we have another word here, right? And then the lights are here in a matrix. So basically what we do is we send the 24-volt power down these lines. So it's like, okay, maybe this light's on, this light's on. And then the rows are where they go to ground. So depending on which rows go to ground and which columns have positive voltage, that's what lights light up. We can actually add a delay into this program here, which will show you how they're actually being matrixed. See that? That's actually what's happening. Like that light's on, then that light's on, and then it's doing more columns too because it's actually doing all 8 rows. So if you could see in super high speed, like that one episode of Star Trek, the old series, you would actually see the lights doing this, but when we take out the delay, it just happens so quickly you can't even see it. And that's matrixing. Whoa. The next thing I'm going to do is make some more geometries. We had our test play field here, and I'm going to cut this whole portion here as a solid piece along with this cave shot. So instead of having these pieces, we can have one big solid piece and try the shots again to make sure we've got our big loop still working here. We've got to find out what these angles are and compare them to the measurements on the board, and then we can redesign a solid piece which we can route out and then put on the board to further along the evolution of the design. All right, so the test geometry that we made before, I've routed into some more semi-permanent pieces so we can try out our big loop in more of the shots, and also this cave shot here. So let's give it a try. Okay, that looks good. All right, it returns to this flipper well. So the next thing I'm going to do here is I'm going to put some just regular targets here, here, and here. So we'll route out these pieces of geometry, put them on the board, and then see if we can hit these spots. Okay, now that we have some basic shots worked out, I'm going to get the 3 systems working, the main program, the sound, and the display. So there's up to 4 lines we have left for inter-processor communications, and right now we have attention, clock, and data. So the CPU will raise up the attention line and then it'll send commands over clock and data to the subprocessors. So I'm going to use those same lines to initialize the processors or the microcontrollers in the beginning. I call them processors because they're processing things for me, so anyway. All right, so it's going to send out a high, and then once the other programs see that, once they're ready, they're going to make certain lines high as well, like, okay, I'm ready, okay, I'm ready. And once they both say they're ready, then the main program is going to continue on its main kernel. So yeah, let's see if that works. That way, when the system turns on, everything will be in sync. So the graphics, I'm just going to call it a processor. The graphics processor and the audio processor, upon boot, are going to wait for the CPU. And then once the CPU sends a signal saying, okay, I'm ready to go, then these things will fire up their I/O routines, and then everything will be synchronized. So to simulate the CPU not booting up, we're going to hold down the reset button on it. Okay, see the command, wait for CPU. Now I'm going to release the CPU, and then after a couple seconds, these should fire up, and the CPU will start sending commands. There we go, see? And we have our lost graphic that we sent, and the music fades in, and the sound effects work. Yeah, so now we just had to figure out why the display is stuck, but yeah, you can see our processors working in harmony. Here's the revision 1 table for the lost. Just cut it. So it's got a lot more geometry, so we can put a bunch of parts on it and have a more playable game to test with. Here at BenHeck Industries, our slave labor force works tirelessly on pinball machines. So here is our revision 2 of the Whitewood for our lost pinball. It now has a ball trough. We haven't fully wired it up yet, but enough to work. And then the sling targets, and then also the pop bumpers. So you can kind of sort of play games now. We need to put in some targets. Once we put in some targets and some more stuff, we can actually kind of start to write the program and build the game up from there. So let me just give you a demo of the game. Right now these will fire and these will fire, and it will make sound effects. And then if you lose the ball, it'll make a disparaging comment and give you a new one. Still working on the sensitivity of those, and then you got this. So the program is sending commands to the sound processor, or sound controller, whatever you want to call it. And then of course you can fail.
Don't ever tell me what I can't do, ever!
And then you get a new ball. So So yeah, it's the basics of building a game right there. So next I'll show you some of the programming features that we use to make this logic work. All right, so let me just show you what the main program here does. The first thing we do every cycle, this repeat means we're going to be cycling. This is the main kernel we have right now, there's not much to it. OUTA IO enable, it sends a high pulse on the IO enable line, and that triggers the timer which enables the solenoids. That's a little glitchy, so the next revision of the board is going to remedy that. Okay, so right down here, I know we skipped something here, but there's a reason for that. These look at the inputs, and basically there's longs or double words, a 32-bit value, and each bit represents a button or a switch being hit. So there's 3 for the bumpers, for instance. We'll just look at 1 for now. If view, general input, bumper switch 0 equals 0, that means if it's pulled low, 0, switch hit. And if the timer equals 0, then bumper timer equals 100, and then we trigger that solenoid. Then we play a sound effect and add the score. Now the reason the timer is important is because we have to, we don't want the solenoid to be on for very long, but we also have to kind of have a debounce. And debounce refers to the fact that a switch kind of flutters a little bit. It's never perfectly on or off. So our version of debounce is as soon as it's touched a little bit, we start a timer, 100 cycles of the kernel before it can possibly re-trigger. Then up here, if bump time equals 0, so that means if bump time is anything more than 0, then we reduce it by 1. If bump time equals 95, so after about 5 cycles, it'll turn off the solenoid. And then once it reaches 0, it won't do this anymore because the variable will be cleared. So basically, like the pop bumper gets hit, that variable set to 100, then it starts counting down. Once it reaches 95, it turns off the solenoid, and once it reaches 0, then you're able to re-trigger it again. 100 might sound like a lot, but in kernel cycles, it's pretty fast. So the pop bumpers can go bam, 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 but it won't get stuck on or trigger itself by its own vibration. And the sling targets work the same way. So what we do when we wire the switches is we have a cheat sheet, so to speak. And we look at the columns and the rows and then write down what each switch does. So yeah, once we have the cheat sheet written out so we know what switches do what, we can just go into the computer and match that up to our variables, and the program will be, once you know, if we write everything down, the program will be easy to do because basically you don't have to be like, if switch 0 equals 1, you can say if left sling equals 1, then hit the solenoid. And the switches that we get that don't have diodes pre-installed, we put the diodes on in this way. See, we have the row, goes into this end, then we have the business end of the diode with the stripe, which tells you which way the current can go. And then we hook it back up to the switch here, and then this, there we go. This switch kind of sucks, but it shows us that we're attaching the diodes in the right way. So now we can wire up the cabinet using the diode switch array instead of just the general I/O. All right, so we're gonna start wiring this up. So we have our switch matrix here, which shows which part of the micro switch to hook up. So the middle terminal will be our column line, and then the row line will be this wire here. So let's say we hook up these 4 ball detect switches. They'll all be on the same column. So if we wire the wires here, we can think of it like this. That'd be row 0, row 1, row 2, and row 3 with one common column line. Okay, I'm ready to rock. I got a whole reel of diodes for the switches. I've got some heat shrink tubing and what's left of my turkey sandwich with Arby's leftover horseradish. All right, so I have these 8 different colors of wire, so I'm gonna use them on the different rows. So not only can I write down what each switch does, but I can write down what color wire I'm using for the rows and columns. So we've got our bundle of wires here, and it's gonna go up into the head to connect to the motherboard. We gotta make sure there's enough length of wire because it's not just a unit like this, but when you lift the board open, it pulls the wires, so you need more slack, and also when you rotate the head down.
The blue one, cut the blue wire!
I'm 50% colorblind. Which one is blue? I don't know what to do. Michael Bay, help me. Oh, I saved Earth from an asteroid or something. The 8 row switches go at the bottom, and then right now we only have 1 column, so that one goes at the top. Okay, so I'm gonna wire this, but this thing's upside down, so I've gotta do it backwards. So I've gotta go
purple, red, blue, gray, green, yellow, green stripe, brown. And then this will be all wired up and ready to test. Now, using 9 wires to get 8 switches might not seem like that much of a savings. In fact, it isn't. But the key is now we can add the next 8 switches with 1 more column. So we have a new column line here, and then it goes to the 8 switches and those return through here. So 1 more wire will get us 8 more switches. And that is the magic of matrixing. So now that the switch matrixing is working along with the machine language driver for it, I will take our old little program that was just flipping the flippers and I'll put it into the new machine language kernel so we can start building the program off of it. So that's what we're going to be working on in the next episode, getting some modes and basic gameplay built into this so we'll have it ready for the show.
Right, that's all the time we have for today. In our next episode, we'll be working on our pinball machine to get it ready for the Midwest Gaming Classic. We'll also have Jerry Ellsworth on as our special guest / arch nemesis. Very well, we'll see you then.
The Ben Heck Show is made possible by our sponsors at Element 14. For more information on all my projects and for a list of all the parts I used today, visit element14.com. We'll see you next time.